Hello, my name is Mikito Nanashima. Today I'm going to talk about joint work with Shuichi Hirahara entitled Finding Errorless Pessiland in Error-Prone Heuristica. Our main contribution is to give an oracle separation between errorless and error-prone average case complexity. So now I explain the backgrounds, especially on the average case complexity. In conventional study in complexity theory, usually study the worst case complexity. This is the complexity of solving problem for any instances. In average case complexity framework, we consider some distribution which generates instance, and we consider the average performance of algorithms. More specifically, we study a distributional problem in average case complexity, which is a pair of language and family of distributions over instances. And we study the complexity of the algorithm solves language L where on average over the choice of instances. But there are at least two standard formulations on this part, solvable where on average. That is errorless complexity and error-prone complexity. And it is also called heuristic complexity. In both models, almost all part is the same. So some instance is selected according to some distribution D, and algorithm needs to solve, so output a correct answer with high probability. The difference is the condition for hard instances. In errorless complexity, this algorithm needs to output a special symbol bot for such hard instances, which represents the given instance is really hard, so I cannot solve it like that. So that's why in errorless complexity, we consider the complexity of solving problems in errorless setting. And in error-prone complexity, we do not consider this additional condition. So this algorithm can output the wrong answer, and we just focus on the success probability of M. Formally, in errorless complexity, the class of visible is usually denoted by AVZ. And we say that distribution problem is contained in AVZ P if there exists some polynomial time Turing machine such that for every instance size and for every confidence parameter, so this algorithm M can output the correct answer with probability greater than or equal to 1 minus a given confidence parameter over the choice of instances. And this M also needs to satisfy the errorless condition. For every instance in support of this distribution, this M output correct answer or special symbol bot. And in error-prone complexity, the class of visibility is usually denoted by here P. So we say that class, so a distributional problem is contained in here P if so there exists some polynomial time Turing machine satisfy the same condition except for the errorless part. And we can easily check that so if some distributional problem is solvable in error setting, then by the same algorithm we can solve it in error-prone setting. And we also define the class AVZ P/poly and Heury P/poly in a similar way. These two complexity notions are really natural formulation for average case complexity, and both have some merit. So especially errorless complexity is equivalent to original Levin's average case complexity theory. And this is algorithmically desirable. Yeah, of course, errorless algorithm is more desirable than the error-prone algorithm. But from the perspective of hardness, the hardness notion in error-prone complexity is stronger than the hardness notion in errorless complexity. And this hardness notion is more suitable for cryptography. Because in cryptography, we usually focus on the success probability of adversary, and we do not care about the errorless condition for adversary. And so one of the central questions in average case complexity is, can we unify these two central average case complexities notion, especially for the central class of distributional NP? More specifically, we define the class dist_NP as a class of pairs of distributional problems, NP problems, and polynomial time separable distribution D. And this question, so posed by Impagliazzo, is stated like this. So can we show the equivalence between these two notions, especially so this, can we show this direction? If we can show this, then we can change the weaker hardness notion in errorless complexity to stronger hardness notion in error-prone complexity, which is required for cryptography. And this is necessary step for cryptography based on the hardness of NP. And recently, Hirahara and Santhanam showed that so this question is also related to another topic in complexity theory, that is instance checker for NP. But unfortunately, solving this problem is a long-standing open problem. That's why so it is really natural to ask why we failed to prove this direction, especially is there any proof barriers? And in this talk, we focus on the relativization barrier. So this question is also posed by the same paper by Impagliazzo. So can we construct an oracle relative to which NP is hard on average in the errorless setting, but easy on average in error-prone setting? I think it is very natural to conjecture that such an oracle exists because there are several intermediate steps to base one-way function on the hardness of NP, but for almost all parts, we can find such a relativized oracle separation. But before this work, we did not know such an oracle separation between these two average case complexity notions. So there was still a possibility that we can show this direction by using only relativizing technique, relativizing proofs. But in this work, we also construct oracle separation between these two notions. And we resolve the open question posed by Impagliazzo. In this work, we also consider a related question motivated by the recent work, which demonstrates capability of errorless average case complexity. Especially so errorless average case easiness is sufficient for some worst case tasks, such as approximating chromograph complexity in worst case sense, or agnostic running for P/poly, or non-existence of auxiliary input one-way function. This is essentially the same as a universal inverter for all given circuits. So this is a kind of worst case task. And this result can be shown by relativizing proofs, and especially the third one has really fundamental proof compared with these two results. And the question is why errorless average case complexity, especially errorless average case easiness, is sufficient for such tasks with worst case requirements. And I think there are at least two opinions for this. The first one is, we assume errorless average case complexity in these two work. So errorless part is really essential. Or the second one is, errorless part is not so essential. And in fact, framework of average case is capable more than we expected. So which is correct? If the second opinion is correct, then this should be able to extend it to error-prone setting. But our result also show that this is impossible by relativizing proofs. So we identify in the previous work, the errorless part is really essential. Our main theorem is stated as like this. So there exists an oracle relative to which on the easiness part, distributional NP is solvable on average in error-prone setting, but on the hardness part, distributional NP cannot be solvable or in errorless setting, even if we consider sub-exponential size of circuits. And solving gap min KT of some meta complexity problem or pack running is hard. And there exists auxiliary input one-way function. In this talk, I mainly focus on these two statements, but let me remark that previously we showed that an oracle relative to which auxiliary input one-way function does not exist, and distributional NP is hard on average in error-prone setting. And our work on this previous work showed that so auxiliary input one-way function and average case error-prone hardness of NP is really natural extension, natural realization of the existence of one function, but these are parallel in relativized world. Especially, we cannot compare the statement directly by only using relativizing proofs. Okay, now let's see proof outline. In this work, for simplicity, we mainly focus on the weaker polynomial lower bound. And our oracle construction is based on the previous oracle construction by Impagliazzo, which separates the worst case and average case complexity for NP. And we modify this oracle to separate these two average case notions. Roughly speaking, the oracle by Impagliazzo consists of a random function for random hardness source and restrictive NP oracle for easiness source. So especially this oracle solves NP in average cases, but not in worst cases. So what we actually did is to subtract the power of NP oracle and we consider more restrictive NP oracle to separate these two average case notions. And in previous work, so for this, we let A use partial information of F, and this is regarded as a random restriction. And so in this work, we let A use more restricted information of F. And for this, we apply a new but really simple type of random restriction. This is a really high level overview of our proof. So now let's see more about the detail. The previous oracle construction have an internal random function for randomness source, which maps n-bit string to, let's say, 2 n-bit strings. And oracle consists of these two oracles, V and A, and this V is a verification oracle for F. So this is determined by a really natural way. And A is a restrictive NP oracle, I explain later. And to separate these two notions, in fact, we need to consider these complexity classes. But in this talk, for simplicity, we consider a simplified setting. So NP machine does not access to a restrictive NP oracle, and we also only consider a uniform distribution instead of all polynomial time sampleable distributions. In this simplified setting, then oracle construction is really simple. So this is a truth table of Fn, and this Fn is selected at uniformly random. And we regard this random selection as the following two steps. So first, we regard each entry, binary entry in this truth table as a binary random variable. Then we first apply random restriction with with non-negligible unset probability, and we select the remaining parts. Then the restrictive NP oracle A is defined like this. So for a given polynomial time non-deterministic computation, especially non-deterministic oracle machine M and input Z, this A regards this non-deterministic computation as the polywidth DNF on these variables by regarding the outer logical or as all possibilities of F and non-determinism of M. Then this A applied the random restriction to this given DNF. And if the answer is determined, then A outputs the same answer. But if the answer is not determined, then this A outputs special reasonable bot. And if the answer is determined, then this output must be correct. Why this work? So roughly speaking, in average case setting, so by applying switching lemma for DNF, we can show that this given DNF is determined only by the random restriction row with high probability. So this yields average case easiness. And in the worst case, so we want to solve NP to B, but for this, we essentially need all information of F, especially if we consider the language L, which asks the ith bit of the variable function. Then this language is contained in UP intersects co-UP, and this is also contained in NP to the B. And in fact, this is a hard problem. Roughly speaking, this is because in almost all cases, so there exist sub-exponentially many x which have superlogarithmically many unassigned points in this random restriction row. So we need to randomly guess such a unassigned point, even if we have the access to A. So to modify this oracle for errorless versus error-prone problem, we begin by analyzing why this oracle is errorless. Especially by the switching lemma, this A outputs the correct answer with high probability. But if the value of DNF is not determined, then this A output special symbol bot. So this part is a source of errorlessness. And if we can change this part to a wrong answer, then this algorithm solves NP on average in error-prone setting. And for this, we naturally let A output 0 for such a case. Because if this A output 1 for false statement, then we can ask A to what is witness for this claim. And we can detect the error of this oracle A, and we can change error-prone algorithm into errorless algorithm. So we naturally let A output 0 in such cases. But this idea is not sufficient for separating errorless versus errorless notion and error-prone notion. Especially, we did not know a hard problem for errorless average case hardness. For example, if we consider the previous language, then this language is contained in UP intersects co-UP. So this language also have witness for no statements. And in such a case, we can also show that we can change the error-prone algorithm to errorless setting. And this problem is not sufficient for our purpose. What is the hard problem for errorless average case setting? Our approach is to construct a heating set generator. A heating set generator is a seed stretching generator such that no efficient adversary can avoid this image of G, in the sense that this algorithm accepts a large fraction, so more than half fraction of strings, but this adversary does not accept any image like this figure. If we can construct such a heating set generator, then we can naturally determine the average case hard problem in errorless setting. So the goal is to construct heating set generator. And the first attempt for this is to consider this F as a heating set generator. But this does not hold because efficiently adversary can access the random restriction row by using A. And this row has partial information of the function, the value of Fx for every X with high probability. And this partial information is indeed sufficient for breaking the heating set generator. A solution to construct a heating set generator is to change a random restriction to prevent such a partial linkage. Especially instead of a standard random restriction, we apply a new but very simple type of random restriction with masks. And in this random restriction, first we randomly select a random subset S of a domain of F, and we regard this random subset as a mask. Then we apply a standard random restriction, but this mask prevents such a random restriction. So we construct a more restrictive NP oracle A by applying this type of random restriction. And for a given DNF which represents the NP computation, so this A apply random restriction, this random restriction to the DNF. And if the answer is determined, then A outputs the same answer. But otherwise, this A outputs 0. Then this A does not have any information of GX, especially for all inputs contained in this random subset. So even with access to this oracle A, so any adversary cannot distinguish the value of GX and random values. That's why, so this by using this observation, we can show that this is a heating set generator, and this implies errorless average case hardness part. But we applied more restrictive random restriction, so we need to consider whether this oracle still works in error-prone setting. But we can show that the answer is yes. So specifically, if we consider this previous oracle as a tilde, then with high probability, this our oracle A and the previous oracle A tilde return the same answer with high probability. And by the argument in the previous work, we can show that this oracle A tilde can output the correct answer with high probability. That's why this yields error-prone average case easiness part. So this is essential idea for our oracle construction, but this is really a simplified case. So for actual construction, please refer to the full paper. I finished my talk with open problems. So especially I share with you open questions where we failed to prove barriers. So which mean that so it might be possible to show such a direction on only the current relativizing proof techniques. The first one is we failed to extend our result to polynomial hierarchy. So that's why it might be possible to bypass these two average case notions by considering more so stronger assumption on pH. And we also failed to prove stronger lower bound. So that's why if we consider a weaker consequence of sub-exponential size of circuits, then it might be possible to bypass these two average case notions. Especially previously, Hirahara showed that the connection between errorless average case easiness of pH and sub-exponential worst case complexity of NP, and it might be possible to extend this result in error-prone setting by using only relativizing proof techniques. So the open question is to prove them or find barriers. That's all. Thank you for your attention.